So in this video, we're going to look at, from kind of a theoretical perspective, solving a system in matrix form. Remember, matrix form looked like this. And what we're going to do is look at what has to be true if A inverse exists. So here's the claim. It says, consider the system of linear equations, AX equals B. So we have a system of equations in matrix form. And the claim is that if A inverse exists, as opposed to not existing, because remember, a square matrix A doesn't need to have an inverse, and we've already seen an example in a previous video where A inverse didn't exist. So the claim is that if A inverse exists, then the solution, so this is an if-then statement, so it'll require an if-then approach to the proof. So if A inverse exists, the solution is two things. It's unique and it's given by A inverse B. So we really have two if-then statements that need to be proved separately. We need to prove that if A inverse exists, then A inverse B is the solution, and then we need to prove that if A inverse exists, then the solution is unique. We have to demonstrate both pieces for the if-then statement. So what we want to remember is that if you from beginning algebra, if you have a statement 3x equals 6, and you claim that something x sub 1, say, is 2, if you claim this is a solution, one way to verify that it's a solution is to plug it in where the x is and show that it actually generates the 6. And if you plug something in and it isn't a solution, you get a false statement. If you plug something in that is a solution, you get an identity. The thing that you plug in generates the guy on the other side. So to show that A inverse B is a solution, what we need to do is plug A inverse B for the x here and show that that gives us B as an output. That will demonstrate that it's a solution. So first we'll show that if A inverse exists, then x equals A inverse B is a solution. So we'll suppose, we won't even suppose, we'll say consider x sub 1 equal to A inverse B. Note that now let's plug A inverse B in where you see the x right here in the equation and show that it actually generates the B. So note that A times x sub 1 is the thing we think is a solution. It's going to look like this. It's going to look like A times A inverse B, but matrix multiplication is associative, so we can regroup the A and the A inverse times B, and A times A inverse is the identity matrix. That's what you get when you multiply inverses, which will be multiplied by B, and the identity matrix times B just equals B. So x sub 1 equals A inverse B is a solution to the equation. So we've shown the first part. We showed that if A inverse exists, then clearly this is a solution. We plug that in for x and it does generate a B. Now we need to show that it's got to be unique. So what we do to do that is we suppose there's some other solution. We'll call it x sub 2. We called this one x sub 1. So now suppose there is another solution, x sub 2. So what do we know? We know because x sub 2 is a solution and x sub 1 is a solution, we know that A times x sub 2 has to equal B, and we know A times x sub 1, we already showed that that equals B. But if they're both equal to B, then by the transitive property of equality, so it follows by the transitive property of equality, it follows that, what do we know? We know that A times x sub 1 has to equal A times x sub 2 because they're both equal to B. And then we simply multiply both sides by A inverse. And we know that matrix multiplication is associative, so we can regroup these. And A inverse times A is going to give us the identity matrix. In both cases, we'll get identity matrix times I sub 1 equals identity matrix times x sub 2. Sorry, identity matrix times x sub 1 equals identity matrix times x sub 2. But when we multiply a matrix times its identity matrix, we just get x sub 1. Identity matrix times x sub 2, we just get x sub 2. And because x sub 1 is x sub 2, we know that the solution is unique. When we tried to assume that there was some other solution, we discovered that the solution was the same as the original solution. So down here, I'm out of space on this page, but I should say something along the lines of, because x sub 1 equals x sub 2, the solution is unique.